This is All India Radio. Power of listening. Under this series, tonight we take you on a journey to the world of yet another magnificent facet of the traditional Indian knowledge systems. I'm Manoj Mainkar. In this episode, we shall be focusing on Bramhagupta's composition law. The expert on the show is Dr. Amartya Kumar Datta of the Indian Statistical Institute, Kolkata. In conversation with him is science communicator Dr. Manas Pratim Das of AIR Kolkata. Stay tuned.
Good evening, listeners. Welcome to another episode of the series Power of Listening. We are delighted to have with us Professor Amartya Datta of the Indian Statistical Institute, who has played a pioneering role in explaining and showcasing our ancient mathematical heritage. He is here with us today to discuss the importance of Bramhagupta's composition law. Welcome, Professor Datta, to our program. To put Bramhagupta's composition law in proper perspective, we would like to start with this question. The contribution of the algebraists of India is one area which probably has not received adequate attention. As we have gathered from outstanding papers written by you, three of the greatest achievements among these are the Kuttaka method of Aryabhatta in 499, a composition law of Brahmagupta in 628 AD, of course, and the Chakravala method of Jayadeva in the 11th century. As we understand, the third one also hinges on the discovery of Brahmagupta. Could you please give us a brief insight into these achievements?
Thank you for this opportunity to share the outstanding contributions of Indian algebraists, especially of Brahmagupta, which, as you have rightly said, is not understood. First, what is amazing is that this composition law, which is quintessence of modern abstract algebra, something which would emerge in 19th and 20th century, as late as that. That is occurring in Brahmagupta's work of 628 in a chapter which is the first chapter on algebra written in known world literature. Mind you, there are other algebraic works prior to Brahmagupta. There are algebraic results in Diophantus and in Aryabhatta, but singling out algebra as a distinct discipline, that has happened for the first time in recorded history in Brahmagupta's work Brahmashfuta Siddhanta, chapter 18, titled Kutakadhyay. That is the first time algebra has been crystallized as a distinct subject of its own. And Brahmagupta defines symbols, how to work with equations, gives the laws of operations with positive, negative numbers and zero, and how to solve equations, algebra of polynomials. These are very basic things which are done at the school level. And the same chapter containing the composition laws. This is an amazing achievement of the human mind, and which makes him colossus in the history of mathematics, and that recognition unfortunately is not there. So this is something which has to be understood, that these composition laws are very advanced ideas in mathematics, and because it is so advanced that in popular discourse on Brahmagupta, or for that matter Indian mathematics, it gets omitted because of its advanced nature. Now, to give an idea about what a composition law means, there are some trivial examples of composition, like addition is a law of composition, that you take two numbers and you produce a third number, 5 and 2, you get 7. Or multiplication is a composition law, that is, you take 5 and 2 and you get 10. So this is a composition law, but these are natural composition laws. These are what you would call trivialities. But more intricate are that you have two polynomials of a certain degree. Of course, you can multiply them, but then you will get polynomial of a higher degree. But the intricate composition law is that two polynomials of the same type, like two quadratic polynomials of a certain type, combine them to get another quadratic polynomial of that type. Like, let us say, dx square minus y square. So dx1 square minus y1 square and dx2 square minus y2 square, combine them suitably to get another form, dx3 square minus y3 square. This is composition law. In modern mathematics, it is very important. For instance, many of you would have heard of elliptic curves. You may not know in detail what an elliptic curve is, but you would have heard that, for example, it has been involved in the solution to Fermat's last theorem. To study the elliptic curve, you define a composition law there that take 2 points on the elliptic curve, then by a certain geometric method, you associate to it a third point, and this association obeys certain laws which are called group laws. And study of modern mathematics involves such structures like which are called groups or rings. So if you go to let us say something like a BSc in mathematics honors, their abstract structures are studied, something like groups and rings. But they study natural composition laws. At a higher level, the MSc level, what they do is they associate groups to certain natural objects, like let us say a polynomial. With a polynomial, you associate a group to understand polynomials better. At a still advanced level, you try to associate a composite law with an abstract structure. So you see that where such defining a composition law to study something, that comes even in our regular studies at a very advanced level. And that is something Bramhagupta is doing in a matter-of-fact way, defining an abstract structure on the solution of equations. So look at dx square plus 1 equal to y square. D is a fixed integer, fixed number, which is not a perfect square. You have to find solutions for that. Now, why one has to find integer solutions of that, I'm coming to it later. But let us take it that you have to solve dx square plus 1 equal to y square. Brahmagupta takes a more general equation. So mind you, this is again too advanced an idea that to solve a certain equation, he goes to something more general. So he takes equations of the form dx square plus z equal to y square. On that, he says, take two solutions on the space of solutions of this. So let us say two solutions, x1, y1, z1 and x2, y2, z2. He gives a rule how to get a bigger solution from that x1, y1, z1 and x2, y2, z2. That is his composition law. Now, of course, what exactly his composition law is, that you can see from various articles, including my article. Let us not get into the exact formulation. But this associating with two solutions, a third solution, in order to attempt the solution of the original equation. This kind of approach you will see in mathematics only after a period of 1000 to 1200 years. So he was amazingly ahead of the time.
Right, Professor Datta. As far we know, Brahmagupta's composition law tackles a particular type of quadratic equation that you have already pointed out. Now, his unique findings appeared in European works since the 18th century, and the equation in question is now being referred to as Brahmagupta-Pell equation. Please enlighten us about this equation and its innovative solution by Brahmagupta.
Yes, you are right. Brahmagupta is the first known mathematician who has taken up this equation dx square plus 1 equal to y square. So what you are calling Brahmagupta-Pell equation is the equation dx square plus 1 equal to y square. Now, to give you a feeling that what is the importance of such an equation, this is a quadratic equation. Before that, linear equations were solved. So linear equation means an equation of the form ax minus by equal to c, where a, b, c are integers, and you have to find x and y, which are again integers. So prior to Brahmagupta, in India, there was a great mathematician Aryabhatta, and he had given solutions. Of course, it could have been older because works prior to Aryabhatta are no longer available. But let us say Aryabhatta had solved this, ax minus by equal to c, where a, b, c are integers, and you have to find integers x and y to find solution to that. That has applications in astronomy, calendar making, in ancient times, and in modern time it is a fundamental step in cryptography or coding theory. Again, if you come to Europe in 1612, Bachet, who comes before Fermat, had solved this equation in a certain book, and that is the book where Fermat You know that there is this anecdote about farmer writing on the margin of a book that I have a wonderful solution of this, that x to the power n plus y to the power n equal to z to the power n does not have any integer solution for n greater than 2, but the margin is too narrow. That book is really that Bash's book. And in Bash's book, he gave this solution of the linear equation, which was done by Aryabhatta more than 1100 years earlier. So you see the parallel that after Bashe, Fermat took up this quadratic equation, dx square plus 1 equal to y square, and in India, after Aryabhatta, Brahmagupta took up the same equation. Now, this is a matter of speculation that why this equation was taken up. But one way of looking at it is, in the Indian context, that right from the Vedic time, there were efforts to write down rational approximation to irrational numbers. So irrational number means, so suppose d is not a perfect square. Like 2, you know that 2 is not a perfect square. There is no integer whose square is 2. So if d is not a perfect square, then root d is not a rational number. That means root d cannot be written in the form p by q. Just as you know, the ratio of the circumference to the diameter, which is called pi, it cannot be written as a fraction. But when we work, we have to take an approximation. So approximation of pi, it is taken to be at least at the school level 22 by 7. For more sophisticated work, you need finer approximations. So if d is not a perfect square, then it can be proved that root d cannot be written in the form p by q exactly. But can you find a good approximation to root d in terms of p by q? That is, find integers p and q such that p by q is a very good approximation to square root 2. Better, find a method which will generate better and better approximations. That means find a sequence pn qn such that pn by qn will be a good approximation to root d, and pn plus 1 by qn plus 1 will be even better approximation. Let us say p by q equal to root d. Just assume p by q is root d. Then what you will get is that p square equal to dq square, right? If p by q is root d, then p square is dq square. But if d is not a perfect square, you will not get p and q such that dq square equal to p square. Then what's the next best you can try? Alter it slightly, that is, be on the lookout for p and q such that dq square plus 1 is p square. So you are arriving at the equation dx square plus 1 equal to y square. And indeed, in India, a mathematician in the 13th century, of course this comes much after Brahmagupta, he did give this method of generating better approximations. So by Brahmagupta's law, given two such approximations, or let us say just you take one particular approximation and keep on applying his law to that, then you will get larger and larger solutions. And that has been described by Narayana Pandit in the 13th century. Now that could have been Brahmagupta's motivation, or it could be a sheer pure mathematician's impulse that this equation is important. He was a great mathematician. He could see that because this is one of the most important equations in history, and he had felt that and he just pursued it. Now coming to Fermat, at the time of Fermat, number theory was not what you would call one of the central areas of research in mathematics. Fermat therefore is regarded as the father of modern number theory. So in the Western tradition, Euclid has some remarkable results in number theory in his book Elements, although it is usually associated with geometry, but there are some remarkable results in number theory in Euclid. Then there was another remarkable mathematician, Diophantus, who explored rational solutions in rational numbers of equations. But after that, the focus was elsewhere, and Fermat tried to revive interest in number theory. And in order to inspire contemporary mathematicians in the area of number theory by showing its beauty, its power, he gave this problem, that find x and y such that dx square plus 1 equal to y square, as a challenge to contemporary mathematicians in order to demonstrate to them the importance of number theory. And so you see, this father of number theory used this equation to kindle interest in number theory, or the generation of number theory to a certain extent owes to this equation. Of course, he also gave many other equations he had taken up, but he did give a special emphasis on this. And the same equation was taken up by Brahmagupta. Incidentally, Fermat, this was a general equation, but he gave some specific numbers also, like d equal to 61, that at least you solve this. But you see, solving 61 x square plus 1 equal to y square is as difficult as solving the abstract one. You cannot get the answer by guess. And curiously, the same example, same problem of solving 61 x square plus 1 equal to y square was worked out more than 500 years before Fermat by Bhaskaracharya in the 12th century. And one of the giants of modern mathematics, Andre Weil, when he was writing about the history of number theory from the time of the Babylonians to Fermat and the later mathematicians. So there, when he came to this theme, he wrote humorously, what would have been Fermat's astonishment if some missionary back from India had told him that his problem was solved by native mathematicians 6 centuries ago.
Your answer has been crawling over the stretch of several centuries and giving us examples of how Indians as well as Europeans tackle these type of problems. But I would like to bring you back to my question where I had asked, how did it come to be known as Brahmagupta-Pale equation?
Yeah, so this was actually called Pale equation. That was a mistake which was made by Euler. Pale has virtually nothing to do with it. If you look at it from the history of Europe, then even if you forget Brahmagupta and Bhaskaracharya and other mathematicians like Jayadev, it could have been called Fermat equation because Fermat was the first who proposed the problem. He didn't give the solution, by the way. So first time the solution was given was by Brownker. He gave a solution without rigorous proof. Brownker was an English mathematician and Wallis was another English mathematician. Wallis wrote a book where he made a detailed discussion about this equation. And in that book, he discussed the work of several other mathematicians, including John Pell. And Euler had studied this book and most probably he mixed up that whose work is who, and he started calling it Pell's equation, though Pell had virtually nothing to do with it. But Euler himself built up the theory of continued fractions in order to put this equation under a framework. So these are clever solutions given by Brahmagupta, Jayadev, Bhaskaracharya in India, and then by Fermat and Brownker. But what Europe tried to do later was to create a theory, create a framework in which this thing finds its place. That was done by Euler. He built up a theory, but he could not complete all the steps in the theory, in the sense that he gave the theorems, but he could not prove all the theorems. And rigorous proofs of all the theorems of Euler in the theory of continued fraction was given by Lagrange. And this entire history, surprisingly, is summarized excellently not in any work in history of mathematics. This is in a book, The Foundations of Indian Culture by Sri Aurobindo. There is a passing sentence which I came across that especially in mathematics, astronomy and chemistry, the chief elements of ancient science, she meaning India, she discovered and formulated much and well and anticipated by force of reasoning or experiment some of the scientific ideas and discoveries which Europe first arrived at much later, but was able to base more firmly by her new and completer method. I had come across this sentence while reading Foundations of Indian Culture, and I was wondering that what's an example of such a thing, and it is only after that that I came to know of these details. And you can see that how the history of this Brahmagupta-Pales equation fits with Sri Aurobindo's description that a mathematician like Brahmagupta had taken up the work which was done in Europe more than 1,000 years. 1100 years, 1200 years ahead of Europe. But when it was developed by Europe, they came as part of big theories.
Right. Listeners, you are tuned to our series Power of Listening, and today we are listening to Professor Amartya Datta of the ISI, the Indian Statistical Institute, as he elaborates on the composition law of Brahmagupta. Now, as we move towards the conclusion of this interview, we feel propelled to ask this question, a question on Bhavana. How is the word Bhavana connected with the work of Brahmagupta? What significance does it convey?
In India, bhavna is a rich Sanskrit word with a whole lot of meaning. So one of the meaning which was used in mathematics is composition. So bhavna means production, generation. So here, for instance, from certain roots, you generate new roots. or you produce a system of new roots. So production, generation, these are certain meanings. But composition, the word is used for composition. For example, in trigonometry, the addition laws in trigonometry, that sine of a plus b is sine a cos b plus cos a sine b. These rules were also called bhavna. So bhavna in Indian mathematics means composition, and it has a spiritual nuance also. That is why when Manjul Bhargava, Fields medalist Manjul Bhargava, when he came to know that Brahmagupta's composition law is called bhavna, he said, what a great word, because it has also a spiritual association. Bhavna is a process of becoming, like bhava. The earth means bhava. Bhavna is a process of becoming, and bhava is the condensed form of that. Anyway, let us not get into the metaphysics. But this term was not used by Brahmagupta himself. It was used by later algebraists. For example, Jayadev, who comes between Brahmagupta and Bhaskaracharya, he used the term bhavna. Bhaskaracharya also uses that. And incidentally, these mathematicians have invariably quoted Brahmagupta's result before stating their solutions of the so-called Pell's equation. Bhaskaracharya calls him Ganaka Chakra Churamani. Ganaka Chakra Churamani, that was the term used by Bhaskaracharya, and that was in 12th century. And recently, in 2000, in a lecture on Ramanujan's birthday, National Mathematics Day, when Manjul Bhargava was asked that who are the other mathematicians in whose work he sees that magical quality which he sees in Ramanujan's work. So he mentioned his own supervisor, Andrew Wiles, and two of the contemporary mathematicians, Barry Mazur and Conway. And then he went back to Gauss. And then he says that if I go further back, then in Brahmagupta, the work that he did in 600, it just blows your mind.
Now, when you mention Jayadeva, the method of Chakravala comes into play, comes into question. So, could you briefly explain what a Chakravala means?
It actually refers to a cyclic method. So it is not very clear that why they called it cyclic method. If you look at the theory of continued fractions, then it becomes clear that there is a certain cyclic process involved there, which would give a hint that maybe they had such a thing in mind where they saw some kind of cyclicity. So that is a matter of speculation because they didn't give that elaborate theory. They just gave you the algorithm. By they, what I mean is Jayadev and then subsequently Bhaskaracharya and Narayan Pandit, they have given the complete solution to what is called the Brahmagupta Pell's equation. Brahmagupta had given only a partial solution which worked for certain integers, but the complete solution was given by Jayadev, Bhaskaracharya. One doesn't know if somebody before Jayadev had, the priority is obscure. But one thing I should make it clear that this Brahmagupta Pell's equation, this has to be thought of as some kind of application. It's a very important equation. But Brahmagupta's this idea of composition law, that is thinking of law of operation in the context of a certain equation, that has to be thought of separately. That idea, that is much more profound than just the composition law. And Brahmagupta's law, it gives rise to an identity, and that is called Brahmagupta's identity. That is something very fundamental in modern mathematics, and therefore what mathematicians sometimes do is that Brahmagupta's result, they summarize it as a certain identity. But that obscures the picture because, see, there are many important identities in mathematics, and Brahmagupta's identity is one such. So one would not realize the value of the Brahmagupta's work if it is thought of just as an identity. The greatness of Brahmagupta's contribution is that he thought of the concept of binary composition as an operation, and it was recognized to be an operation. That is why the term bhavna was given. I'll give you one example that Manjul Bhargava, when he first, incidentally, Brahmagupta's work was generalized by Gauss. So Brahmagupta worked with quadratic forms of y square minus dx square. And Gauss worked with general quadratic forms ax square plus bxy plus cy square and gave a composition law on such forms. And 200 years after Gauss, Manjul Bhargava, giving a simplified way of looking at Gauss's work and which produces new composition laws which nobody imagined before. That is what made Manjul Bhargava famous. Now, that was in 2001, just 200 years after Gauss. Now, Manjul Bhargava, when he initially wrote about his composition laws, higher composition laws, he mentioned about Gauss, but he had not mentioned about Brahmagupta because he had also, like other mathematicians, thought about it as an identity. But later, when he realized that this was thought of by Brahmagupta as an operation, his perspective will change, because if you see that after 2004, he invariably mentions Brahmagupta in his lectures. And Brahmagupta is bracketed with, mathematicians of 19th century. When he acknowledges his predecessors, that he has been standing on the shoulders of his predecessors, he mentions Brahmagupta, Gauss, Dirichlet, maybe Eisenstein, and then Dedekind. So they are all 19th century mathematicians. And with them, 7th century mathematician is bracketed. So that is where his work lies.
Right, Professor Dotto, we thank you for taking time out of your extremely busy schedule to enlighten us about the contribution of Brahmagupta, his composition law. You have raised our expectations to such a level that you leave us today with an yearning to know more about this topic. Thank you and goodbye.
Brahmagupta's composition law. You heard this episode of our all-new series on traditional Indian knowledge systems, Power of Listening. The expert on the show was Dr. Amartya Kumar Datta of the Indian Statistical Institute, Kolkata. In conversation with him was Dr. Manas Pratim Das. This series has been conceptualized by Shashi Shekhar Vempati, CEO Prasar Bharati, and produced by Dr. Manas Pratim Das and Vinod Kumar. Special thanks to AIR Kolkata, Amol Parth and Randhir Thakur for their contributions. This episode is also available on our official YouTube channel, Akashvani AIR. We shall be back next week, same time, same frequencies. This is Manoj Mindkar signing off from Delhi. Bye for now.